Picture this. You are maneuvering a multi-million-dollar offshore supply vessel within mere meters of a fixed drilling platform. The winds are howling, the waves are crashing, and the stakes could not be higher. Welcome to This Explainer, where today we're looking at one of the most incredible high-wear acts in the modern maritime world, dynamic positioning, or DP vessels. Keeping massive, heavy ships perfectly still in raging seas requires absolute, flawless synchronization between cutting-edge automated systems and highly trained human operators. Let's dive into how it actually works. All right, let's treat our agenda today like a pre-watch safety briefing. We're going to run through 1. The basics of DP vessel safety. 2. Operator competence and those Category A and B designations. 3. The role of our engineers and technicians. 4. Doing a real check with a DP footprint. And finally, number 5, the transition to manual control. Section 1. Basics of DP vessel safety. The foundation of station keeping. Okay, put yourself right on the bridge of a massive ship for a second. When an offshore supply vessel is out there doing its job, transferring heavy deck cargo, dry bulk, or hazardous materials, it operates precariously close to these giant offshore installations. We are talking about unbelievably tight margins of error here. Out on the water, they call this close proximity time. And in these zones, exact positioning isn't just about operational efficiency. It is literally a matter of life and death. One wrong move and the vessel drifts into the platform, causing a catastrophic incident. So to manage that immense risk, the industry relies on a unified framework. The absolute heart of this is the dynamic positioning, or DP system. Think of it as a highly complex setup that combines power, thrusters, and control systems to automatically keep the vessel's position and heading locked in. But, you can't just slap a computer on a boat and call it safe, right? The global gold standard for safety here is the IMO MSC/CIRC 645. Published way back in 1994, this document is basically the ultimate rulebook. It sets the design criteria, dictates the necessary equipment classes for redundancy, and outlines the strict operating requirements that vessel operators must follow to protect the crew, the ship, and the environment. Moving on to Section 2, Operator Competence, Category A and Category B watchkeepers. Now, a DP operator doesn't just sit there and push buttons. No way. They have to process an absolute mountain of real-time data. We're talking inputs from multiple position reference systems like DGPS and laser fan beams, wind sensors, individual thruster outputs, the whole shebang. Sure, the machine makes the micro adjustments, but the human has to understand exactly what that machine is doing, why it's doing it, and even anticipate what it's going to do next. Because of this, the competence and training requirements for these operators are incredibly stringent. Because the stakes are so high, the responsibility of operating these systems is actually split into two specific categories of DP bridge watchkeepers, Category A and Category B. Category A, that's your highly experienced master or navigating officer. They're fully certified, they've got tons of time on that specific vessel type, and they are deemed fully competent to run the DP system completely unsupervised. Plus, they are experts in manual ship handling when close to an installation. Then you have Category B, which is usually a junior navigating officer. They are trained and can operate the system, but only while supervised by a Category A operator. But here is the critical part. Even a Category B operator absolutely must be trained and ready to instantly take manual control and safely move that vessel away if things go south. Section 3. Role of engineers and technicians, the unseen guardians. Listen, without power, the smartest computer on the bridge is just a very expensive paperweight. To keep these power systems alive and the vessels safe, engineers, electricians, and electronics officers need some seriously specific technical knowledge. They have to deeply understand the vessel's DPFMA, that stands for Failure Modes and Effects Analysis, meaning they need to know exactly what happens if even a single component fails. On top of that, they handle the constant maintenance and monitoring of the power generation systems, the power management systems, and the UPS, the uninterruptible power supply. In fact, when the ship is within that 500-meter zone of an installation, an engineer has to be on watch in the engine control room at all times, and they are strictly forbidden from doing any routine maintenance that could mess with these critical systems. The guidelines specifically state they must ensure there is a first level of response to a problem on the DP control system and power generation. So engineers aren't just mechanics turning wrenches down there. They are really the unseen guardians of the ship. If an alarm goes off regarding power generation or the DP interface, they are the first responders. Their rapid diagnosis and action down in the engine room are exactly what give the bridge officers up top the time they need to make split-second, life-saving decisions about the vessel's positioning. Section 4, Real Check, DP Footprint, Theory versus Reality. Okay, let's talk about the DP capability plot. This is a theoretical, computer-generated polar diagram. Basically, it calculates how well the vessel can hold its station based on assumed propulsive power against forces like wind, waves, and current. It shows you the expected performance if all thrusters are working perfectly, or what might happen in a worst-case failure scenario. Now, these plots are absolutely crucial for risk assessment and figuring out safe working limits before a vessel even gets near a platform. But, and this is a huge but, they are theoretical. It's math based on assumed variables. And as we all know, theory only goes so far out on the ocean. Enter the DP footprint plot. This is a concentric scale used to manually record actual observed movements. The guidelines heavily recommend doing regular performance checks using these footprint plots. The master and the DP operators should be charting these basically whenever they get the chance. By plotting exactly where the ship drifts relative to its target position over time, they get a physical record of how the vessel actually handles current weather conditions. It shows the true tightness of the vessel's positioning circle, taking into account the real-world performance of the thrusters and the actual, rather than assumed, environmental forces. So, what happens when your beautiful, perfect, computer-generated capability plot contradicts your messy, real-world footprint plot? Well, the rules are absolute. Actual measured performance always overrides theoretical calculations. If the footprint shows the vessel is struggling to hold position in 20 knots of wind, even if the capability plot promised it'd be completely fine up to 35 knots, you trust the footprint. Practical data logged by the crew always trumps theoretical paperwork. If there's a significant difference, operations have to be adjusted immediately, and those theoretical plots might even need to be officially modified. Which brings us to our final part, Section 5. Transition to manual control when automation fails. Paint a picture in your mind for a second. You are 50 meters away from a massive steel structure in the open ocean. Suddenly, the wind shifts, a huge swell hits, and at the exact same moment, you lose your primary position reference systems. Alarms are screaming on the DP console. The automation has completely failed or degraded past safe limits. In a fraction of a second, the watchkeeper has to shift from being a passive monitor watcher to an active, hands-on ship handler. This terrifying scenario is the exact reason why those Category A and B competency standards we talked about earlier are so unbelievably rigid. When this happens, the guidelines dictate a very clear order of operations for the watchkeeping officer when switching from automatic to manual control. Step 1. Assess the immediate risks. They have to know exactly where the wind and current are going to push that vessel the second automated thrust drops. Step 2. Hit the switch from auto DP to independent joystick or full manual controls. Step 3. Use raw ship handling skills to safely maneuver away from the installation and completely get out of that 500-meter safety zone. Only after the vessel is safe and the fault is identified and fixed can they think about returning, which leads to Step 4. Before re-entering that zone on automatic, they have to do a full suite of DP location setup checks right from scratch. We build these incredibly complex, redundant, brilliant machines to keep vessels safe in some of the most hostile environments on Earth. But perfect systems? They simply don't exist. So whether you're navigating an offshore supply vessel or just navigating our increasingly automated modern life, it leaves us with a pretty provocative thought. When the automation inevitably fails, are you trained, competent, and ready to take manual control?